But yeah, as mentioned, I'm Stan Seibert. I'm the Director of Community Innovation at Anaconda. That means I oversee our open source projects, but I'm also one of our subject matter experts on GPUs. So just a quick bit about Anaconda. We were founded in 2012. We're based in Austin, Texas. You may be familiar with the Anaconda distribution. This is a free distribution of open source packages for data science on Windows, Mac, and Linux platforms. It has about 6 million users. Hopefully some of you in the audience are part of that 6 million. People often ask me, how do you guys make any money if the Anaconda distribution is free? We do other things for pay. Anaconda Enterprise is a enterprise software platform that we sell to organizations to help them develop, govern, deploy AI and ML projects and sort of coordinate teams in their organization. In addition, we do training consulting and open source, both funded by the company as well as funded by external parties. So I'm going to talk a bit about deep learning, but deep learning is machine learning, and I find it useful to start with the what are you trying to do so you don't get caught up in the technology. And fundamentally, with machine learning, what you're trying to do is take data and some domain knowledge, and I like to emphasize this because I am very scared of data scientists analyzing data they don't understand. Even if it's at the level of I understand how text is messy, that's still domain knowledge. So it's really important as a data scientist to know something about the data you're analyzing. So when you combine those two things into your machine learning process, this is both a combination of algorithms and techniques that you use, your goal is to produce a model which you're going to use for some purpose, whether it's prediction, classification, whatever. And so when we talk about deep learning, we're talking about swapping out that middle thing. It's not going to give you, deep learning will not tell you about your domain, you will have to know that yourself. It's not going to create your data, you have to have that from somewhere. But it helps you potentially, in some cases, do that middle part. And as if you've been paying attention during this conference, you've seen all kinds of things that machine learning can help us, whether it's from predicting the future, revealing hidden information, finding structure in large data sets, identifying unusual trends. These are all things that machine learning does, and they are things that you can also do with deep learning. So deep learning is really just a specific technique for machine learning in which the model is structured as a bunch of layered computation. In particular, each layer, so each one of, this is the Google Inception v3 network drawn out schematically. Each one of those little colored bubbles is a layer which actually constitutes many parallel calculations happening, which then feed sequentially into the next part of the network. And this way of laying out a calculation turns out to be very generic, but also very trainable, surprisingly trainable. The surprise in the deep part of deep learning is the fact that it was not thought for a long time that you could have a network with this many layers chained up and still be able to train it reasonably. It turns out you can, even though it has 24 million parameters, which in my past life as a particle physicist, if you told me your model had 24 million parameters and you were going to fit it, I would think you were crazy. But it is possible. And there are lots of examples of things that you can do with deep learning. Some of the more interesting ones combine data sets. So for example, image captioning, where you're taking images as an input and producing text as an output, is one of the more interesting problems that's very hard to do with other techniques. So in this case, to improve image search, Google built a network using Inception v3 as it happens, to be able to take images and add a caption to them and then word search on that caption rather than rely on humans to have put text context around the image when they scraped it off the web. Another one is time series analysis. There are plenty of talks in finance and other things about trying to model various time series, whether in financial markets or other things, using RNNs, which are recursive neural networks. One of the other interesting uses of deep learning, especially GPU-accelerated deep learning, is what they call style transfer. So on that list of different things you can do with machine learning, I actually didn't talk about this one, which is to, instead of trying to extract information out of your data, is to generate new data. In this case, what you are trying to do is, say, train a model on a particular painter's style, whether it's Picasso, Van Gogh, Monet, something like that, and you want to produce from an input painting, a version of that painting effectively sampled from the distribution of Picasso. You can imagine that there's a space of paintings that Picasso could make. I would like to find the one that looks the most like the Mona Lisa. And so in effect, you're using this model to produce new data. And this can be really interesting for simulation tasks and for other things that, again, would be sometimes hard to do with other methods. So if you're aware a bit about neural networks, I remember when I first learned about neural networks long ago, they were described dismissively to me by my AI professor as the second best way to do machine learning. But the advantage was the second best way to do any kind of machine learning. But he was intending that as being, you should go find the best way. In the intervening 10 years, things have changed a lot. And neural networks came back, they got a new name, now we call it deep learning, maybe to forget all of the 40 years of failure that neural networks had. But what changed? Why did there was a sudden explosion where you went from hearing basically nothing about it except for in certain research areas to being all over the place on the news, all this stuff? And it was really the convergence of 4 factors. Much bigger training sets, the explosion, in some sense, big data kind of helped to precede, I think, a lot of the success in deep learning because you first had to acquire all of that data to be able to train with it. 2, a lot of the best, in fact, basically all of the best deep learning tools were being developed as open source, which meant that researchers could see what the other one was doing, innovations could propagate very quickly through the community. Another thing was that actually that last one feeds into algorithm research. It wasn't just do the same thing you did in 1980, but faster. You had to do new things and different things. And then finally, faster and specialized hardware. Moore's law combined with some serendipitous hardware developments not really intended for deep learning, but turned out to be useful for it, helped us get here. And so if you're in this talk, you're probably interested in that upper right corner about the faster and specialized hardware part, and that's where GPUs come in. So how do GPUs help? When I talk to people about GPUs, I've been doing GPU computing for about 10 years now, a lot of people think that GPUs are somehow some kind of like magic thing that just makes everything faster or something. And the thing to keep in mind is that NVIDIA's developers are not somehow smarter than Intel's engineers. I mean, it's not like people at NVIDIA suddenly had this aha moment and then they made computers 20 times faster. That's insane. What they did is they operated with a different set of constraints. All engineering is about constraint trade-off. So your typical CPU is basically a general purpose computing device. It's designed to run everything from your operating system to Windows to TensorFlow. And so you can imagine it's sort of like a car that you can use to drive to the store, deliver boxes, do what you need to do. A GPU, however, is much more specifically oriented around parallel computing. And parallel computing with a lot of restrictions. So I like to think of it as this tractor here. You would not want to drive this to the store or deliver packages with this. It's not even street legal, but I mean, there are many issues with this. But for the thing it was designed for, in this case, tilling a field, it is incredibly effective. And it does, 30 rows at a time kind of thing. So that's the thing to keep in mind, is that by its very nature, the fact that GPU is useful for you means it's also limited. So instead of looking at cars and tractors, what's going on inside of this chip? And basically what is inside of a GPU, here I'm showing a schematic diagram of the Nvidia Titan V, which is, I think, still the fastest option you have, although the RTX cards just came out a few weeks ago. What it is it's basically an entire chip oriented around parallel math. There are a lot of things in a regular CPU that are designed to help you do other stuff, caching, all kinds of stuff. The idea here is that, in fact, the GPU throws out a lot of that. It has a ridiculously tiny amount of cache. But it has an enormous memory bus, and it has an enormous amount of floating point units. And those floating point units don't need a lot of support logic because they're running the same instructions together on different pieces of data. They're not all independent. So if you ever look at the CUDA documentation and you see them talk about things like CUDA threads and whatever, the first thing you have to unlearn is that when NVIDIA says thread, they don't mean what you mean as CPU thread. On a CPU, you're used to thinking of threads as being independent execution contexts that can go every way they want. CUDA threads have to stay in sync in groups. And if they diverge, you will get lower performance. And if they diverge a lot, you will get horrible performance. So this is not a 4,000 core CPU. This is a different beast. As I'm mentioning here, there's no free lunch here. GPUs make assumptions. These assumptions happen to work well for deep learning, but as you think about other ways that these might get applied, it's useful to keep them in mind. In particular, GPUs have a very wide memory bus, but they're constrained by their connection to the CPU. So you can build a workstation with hundreds of gigabytes of RAM, but the biggest GPU you can get currently has 32 gigabytes of RAM, which means that the data set that you're trying to at least work with while you're training ideally should fit in that space. Now, it doesn't have to, but that's sort of the best case scenario. The data needs to be read in a parallel and mostly sequential fashion. Again, for something like deep learning, where you're doing a lot of parallel calculations in each layer, that's not a hard constraint. The computation is data parallel. You want to do the same thing at the same time to many data elements. And you want inter-thread communication and synchronization to be infrequent. If you're used to parallel computing on the CPU, you might be familiar with things like locks and semaphores and all of these other things. In general, those constructs, while possible on the GPU, are performance death. You really want to stay away from those. And so if your problem fits into this space, you're golden. And when I started, I got my first 8800 GTX card for scientific research, I basically found all of the problems that we were doing that fit these constraints. The memory was much smaller back then, with almost no exceptions, and it was great. But as soon as you stepped outside of that, performance started to fall off. Now, in the intervening years, they haven't just made GPUs bigger, they have given you more tools to bend the rules. And so really the trick to what I would say a good GPU programmer is knowing how to bend these rules to solve a bigger range of problems than just the trivially parallel ones. Now, there are a lot of trivially parallel problems, which is great, but you can do more things with these. So the nice part for you as a data scientist is you don't actually have to know what these tricks are. You don't have to worry about that. The authors of deep learning libraries know these things. They work with companies like Nvidia and incorporate that knowledge into their libraries, so you don't have to necessarily worry about that. However, if at some point you want to start using GPUs for other things like simulation, I've gotten a lot of mileage out of Monte Carlo simulation on the GPU, you may start having to dive into some of these lower issues. So as a result of this, it's easy, it's you can frequently achieve speedups of like 5 to 20x over multi-core CPU training with the GPU because of the advantages that the GPU has. So why don't you have to know all these details? It's because there's a layering of abstraction going on. So you could be running your deep learning on multi-core CPUs or really high core count CPUs like the Xeon Phi or on GPUs. It doesn't really matter to you because above that layer, there is a layer of what I would call primitives. These are the sort of fundamental operations that you use in a deep learning application that have been implemented for you usually by the hardware vendor. So Intel makes MKLDNN, cuDNN is made by Nvidia, MIOpen is made by AMD. These are libraries that do all of the math as efficient as the hardware manufacturers know how to do. And then on top of that, to do neural networks, you need to have a layer of what I would call tensor math. And so tensor math is basically, if you're familiar with NumPy and working with multi-dimensional arrays, that's effectively in this case, what tensor math means. If you're a physicist, you are thinking about tensors as something else that's not that. And so that sort of, again, forms a higher level of math building block. And then on top of that, you're saying, okay, I'm gonna do, computations with a bunch of array operations. I'm going to chain them together to make my neural network. I don't actually want to worry about those details. I just want to say I want a convolutional layer, or I want a pooling layer, or I want a dense layer. I want to sort of describe my network at a very high level. And at those highest levels, you have some of these things like PyTorch span that. TensorFlow is basically incorporating the Keras API directly into TensorFlow. MXNet, again, has both high and low. If you're familiar with Chainer and CuPy, they're probably maybe the 5th most popular deep learning library. CuPy is actually NumPy entirely rewritten for the GPU, and a pretty big amount of NumPy. So if you've ever wanted NumPy in the GPU, I would strongly suggest you take a look at CuPy. The other nice thing about all of this is that you don't actually even have to have it in your physical computer. GPUs have finally become available on basically every major cloud. If you're interested in learning, honestly, and I'll talk a little bit about this later, you don't need to necessarily go to the cloud or get Tesla cards or any of that stuff. There are much cheaper cards that are great for learning. If you're trying to maybe do things a little bit faster or get into production, that sort of thing, you may want to go this route for more reliability and uptime. I would generally avoid the K80 except for demos or something. There, as you move across this chart, the P100 is about 5 times faster than the K80, and the V100 is about twice as fast as the P100. So there's a lot of advantage to not doing this, although these are cheap. And not that I'm paid by them, but Azure and Google Cloud tend to be cheaper than AWS. So if you're looking to save a little money. So how do you get started with deep learning? This is probably the most common question I get. And the great thing is that it's easier than ever, but before you put your hands on the keyboard, I strongly suggest you think about what you're trying to accomplish so that you know when you're done. Because the worst thing that can happen here is iterate forever and never really know if you succeeded, because then what have you accomplished? So this is my public service announcement. Before you start, ask yourself, what is the purpose of the model you are trying to create? It's not enough to just shove a bunch of data into a neural network and then get out some numbers if you have no point. Specifically, the problem is that, okay, I want to, make more money in my business. So that's not very specific. Okay, I want to reduce, angry customers. Okay, that's still not quite specific enough. You need some kind of quantitative model output that will help you. So maybe you say, I want to have a score assigned to every customer support request that tells me how angry this person is, and maybe prioritize them or something like that. That's now a quantitative thing you can try to achieve. Another thing, and this is the great part about the internet, is are there publications, blog posts, conference talks, et cetera, describing a similar use case? It can be really daunting to look at a blank notebook effectively and say, how do I start with my network? The best thing you could do here is literally Google something like Keras plus the use case you care about and go find other people who have solved the problem. They will give you, they may not work for you, but they'll at least put you in the ballpark. And you'll have some idea of roughly what kinds of networks have been successful for people. If you do that and you see no hits, you recognize that you might be on a research frontier that may not be feasible for you depending on if you're a graduate student, that's great, open season. If your boss wants a solution by Friday, you may not want to do that problem. So always look for related research. The other thing is also to know what data is available to you and can more be gathered. Because often you may find that you start working with your model and things are going and things are looking a little bit promising and then it just kind of peters out and you're like, man, if I could double the size of this data set, maybe I would have a chance. It's good to know before you start whether that's even possible so you don't go chasing yourself in circles to find out actually I can't get any more of this data. The other thing here, and this is I think not appreciated enough, is there additional domain knowledge that would be helpful for selecting training data? So for example, if you're trying to score loan applications, go talk to someone who has done that manually and ask them what they looked at. It may be obvious, you may be like, okay, clearly we're looking at the same data, but having some intuition from a person who has solved the problem manually already can ensure that you're not reinventing the wheel and rediscovering how credit risk works all by yourself. Another thing, and this has come up a lot in the conference, thankfully, is are there security or ethical concerns associated with either the training data or the future uses of this model? You want to ask this question as early as you can, because it's easy when you get going, as was mentioned in the last talk, to just keep going because you've already the sort of sunk cost fallacy. You start rolling on this thing, you're using a bunch of data that you could never get because it violates the privacy of so many people, and you're basically building a model you can never deploy because it would fundamentally be unethical or violate the law. So you want to start with understanding what are the caveats. If you're going to use this data set, what are the legal constraints? What are the ethical constraints? What is this model going to be used for? You want to understand all of these things so you don't just start going because you don't just keep going because you started down the wrong path. Another thing that people forget is what accuracy has your organization already achieved? So if you are building a model and you're like, great, I can get 90% accuracy on this credit risk model, and you found out that the existing models using logistic regression already get 95%, then you haven't really achieved anything. But the other advantage is that tells you when you can stop. If the current model is 80% and you hit 90, then actually maybe you're done. You don't have to keep fussing around with things. That's where these other things come into handy, like can you quantify the benefit of the accuracy? Is an extra 10% going to save you $1 million or save you a week or a month or a year? Knowing those trade-offs help you decide when to stop, and that's the most important thing, is to know when to stop. And then finally, the goal of the model is to be deployed. What is the deployment environment? Do you even have a GPU? And then once it's deployed, how do you know if it's working? So having said all of that, which honestly applies to both GPU and non-GPU machine learning, technically, if you want to get going with this, what do you need? So my recommendation today is you want an Nvidia GPU. There are other GPUs, but I don't think they're quite ready or as easy to use yet. Your best result is with something, and apologies for using the architecture technical names. You can Google and see what these mean exactly, but the suggestions kind of cover it. You want Pascal, Volta, or Turing, basically, as sort of the generations of GPU. In particular, because with Pascal, they started introducing features in the cards that specifically target deep learning. And so the difference between Pascal and pre-Pascal is quite dramatic. That was that 5x that I was talking about. You want at least 4 gigabytes of GPU memory, I think, for any reasonable deep learning applications. And so here are some model numbers that I would suggest. And if you are just learning, go for the GeForce cards. They have basically the same capability. They might be slightly slower. They might break on you. But the price difference means if they break 5 times, you've still paid less than a Tesla card. So I got through my PhD basically cooking GeForce cards. Worked quite well. Your boss may not be so excited about that, so maybe in production you should look at the Tesla cards. CPU, you don't want like a Raspberry Pi hooked to this $1,000 card. You're going to want a quad-core CPU, and you're going to want it to have more memory than your GPU, probably 2 to 3x, because your data has to start there before it gets on the GPU, and you need some room to do data processing. Also, another thing is people often ask, can I do this? Which operating system? I would honestly say, if at all possible, use Linux. Your life will be better. And I'm not just saying that as some kind of Linux partisan. There's some deep, especially if you're using the GeForce cards, there are some deep limitations to GeForce on Windows due to the way the drivers have to work. So I would suggest that Windows does work, however, if you have no other choice, that is possible. Mac, I'm using a Mac right here. It makes me sad every day that there is not an Nvidia GPU in here. There hasn't been one since 2014. So I have like the last model, and I can't really do deep learning on it, but I do other stuff with it. So you can also use the cloud, although that can get expensive if you're learning. I do say all of this, though, that this isn't a static thing. AMD support is developing rapidly. I was building AMD GPU packages for TensorFlow before I came to this conference. They're working on catching up. So someday this list may say NVIDIA or AMD, but still Linux. All right, so once you've got the hardware and operating system, all that sorted, one other note. It's really important on Linux that you have installed the official NVIDIA driver. You don't necessarily need the CUDA SDK, but you need the graphics driver that NVIDIA makes. Ubuntu ships with something called Nouveau, which is a third-party open source driver that does not really work with CUDA. So you have to go get the real one. All right, so let's say you have an Linux machine, you've installed the NVIDIA driver, now what do you do? And now, honestly, not just because I work there, I would say the best thing for you to do is go download the Anaconda distribution. It's free, it includes 700 packages, not necessarily in the installer, but on the online repository. Conda Forge has several thousand more. It is by far the easiest way to get all of the different data science packages, which might cross languages and all kinds of things, onto your system. I mean, we basically invented Conda 6 years ago because we realized we couldn't get all this stuff installed on our computers easily. So take advantage of that. There's a lot of work behind the scenes that goes into making this distribution work. In Anaconda, we have a number of GPU accelerated packages. So the issue here is that not every package is automatically GPU accelerated. You need to turn it on, compile it with certain flags set, that sort of thing. And so we do that for a number of packages, in particular the ones on this slide. Interesting thing to note, XGBoost is not about deep learning, but you can also GPU accelerate boosted decision trees, and that's now available. Numba is also not about deep learning. That's actually a project I work on. That's a Python compiler, which is usable both on the CPU and GPU. So if you want to talk about Python compiling, come see me after. I mentioned Python. I would say if you're getting started with this, although there are ways to do all of this in C++ and many other things, I think Python is the best way to get started with this. Most of the examples are in Python. Python's a relatively compact language to write, and it's supported by basically every framework. It has kind of become the de facto language of deep learning, just sort of both due to supply and demand pressures there. So here's a bit of a model both in TensorFlow, like raw TensorFlow, in Keras, and in PyTorch. The syntaxes are different, but honestly, once you're sort of conceptually plugged in with what all the stuff means, the syntax differences maybe take you a couple days to pick up the differences. So I mentioned Keras. If you're getting started, I think this is the #1 easiest way to get started. I love this library. Actually, reading their documentation is like getting a mini lesson in deep learning. They link back to papers. So if you're looking at all the different layer types, they link to the papers that justify why you do that. The optimizers, they link to that. So I think it's a great place to start. Just go to this page and start reading through this sidebar, and then maybe click on papers if you're interested in going deep. The other thing is Jupyter Notebooks. You may already be familiar with this. I love using Jupyter Notebooks for this kind of thing. Jupyter Notebooks are not great for software engineering, but they're great for data science experimentation because you can combine code and text, like you can write notes to yourself so that future you knows what you were doing or what you were thinking, and plots, and all of that into one coherent artifact that you can version control and all of those other things. So a lot of times you can, and there's nothing stopping you in a Jupyter Notebook from using the GPU. It's not, the kernel has to be running on the machine with the GPU, but that's, it's like anything really. All right, so you've fired up your Jupyter Notebook, you've got Keras installed. What are you gonna do? So the first thing you have to do is data prep. You need to split up your data set into at least 2 or 3 pieces. You don't want to overfit your data or bias your results by using the same examples for training and validation. That's a good way to fool yourself. This whole pipeline, however, is not really being done on the GPU, and it's not really involving the deep learning frameworks. This is often just standard Python. I would strongly suggest if you don't know NumPy to learn NumPy because a lot of this data prep involves NumPy, plus any other Python libraries you might use. But that's, again, one of the reasons that Python has become popular for this is it's got all kinds of libraries to help you do these first stages before you actually get to the deep learning part. Another public service announcement, it is really easy to fool yourself with data. Both your training data can be non-representative of reality. You might, collect a subset, and so, cases out here are not, your model's never trained on, you're not actually uniformly sampling the whole space. And the other problem as mentioned is the non-stationary distribution problem. Since you're probably not measuring properties of nature that are static, you're measuring the behavior of people, which is quite dynamic. The behavior of whatever your data is may change over time, and so you may need to rerun. This is another case actually why GPUs have become very popular, is they let you retrain on large data sets more frequently, which might be necessary to track the drift in your data. And also don't fool yourself, your data has this problem. No matter what data you got, no matter who you got it from, and no matter how much you cleaned it up, at some level you have this problem and you just don't know exactly where. So you should always be prepared for this. So you might, preparing to load some data. This is again why you want, a couple of CPU cores because this is all happening on the CPU. In this case, Keras comes with some nice sample data sets. Again, if you're learning, I would suggest checking out the CFAR10 data set, which is a bunch of very small color images that have 10 categories that they're a part of. It's better than the MNIST digit set, which I think is too easy and can be solved with not deep learning. So you kind of want to start with something a little bit more fancy. But the data prep, again, in your notebook, you have a record of what you did. A lot of this is NumPy operations. Occasionally you come down here, Keras does include some data prep utilities. They still run on the CPU, but they're useful to convert a column that's like a category number into one-hot encoding and that sort of thing. Again, take a look at the Keras manual for stuff there. Defining the network, CPU, GPU looks the same. And one of the themes I hope you take away from this talk is that using a GPU, aside from the difficulty of getting the hardware, is not a lot of change on the software side. Things like Keras and TensorFlow abstract much of that away from you. And so there's a little bit of thinking you have to do about the GPU, but not a whole lot, which is great. You can start out without a GPU and then switch to one, although a lot of non-trivial models take so long on the CPU you might not bother, so I wouldn't wait too long. So this is describing a very simple model here to try and take an image. This is from CFAR10, that's an ostrich bird. It's classified as a bird. Actually, if you look at this data set, there are some really blurry pictures that as a human I can't even identify. And you push it through, this sequence of layers defined here schematically kind of looks like that. And out will come a category like bird. One other nice thing, and this you can still, this may let you get away without having a GPU, but it also can be beneficial on the GPU, is you can build on existing models. So Keras gives you a way to download pre-trained models. Like, so for example, Google has taken their GPU farm and trained ImageNet, which has millions of images and all of that. You can get a network already pre-trained on ImageNet. And then if you want to use that, oftentimes the earlier layers are useful for problems that they weren't originally designed for. They weren't initially trained to identify currency or something like that, but they often in the early layers will be identifying abstract sort of shape patterns that you could combine in a different way to identify currency. So what you can do, and this is called transfer learning, is load a pre-trained model, chop off the last layers, and retrain just these 3 dense layers to satisfy your categories. So you're not training it for whatever ImageNet was trained on. You say, I have 10 categories because I have 10 kinds of currency I want to identify. That's a very straightforward thing to do. The other nice thing is, starting from this point, you can even retrain all the weights in the whole model on your GPU, and that, if you start from the pre-trained ImageNet state, you often can converge reasonably. I've done experiments where I've started from random weights on a network this big and gotten nowhere with my data set, but starting from ImageNet, I was able to converge on a reasonable solution with my data set, even though, because I just didn't have enough data in time. So you can often cheat a little bit and start from not a completely random point in space, but one that's maybe closer to being useful. So training a network, again, this isn't GPU specific, is basically you define a loss function, you supply your training data, and then the built-in optimizer, Keras has a number of them, TensorFlow, all of them, basically compute the loss function, work backward through the network through a process called backpropagation to update the weights, and then run the network through again. And this is what's basically happening, is that computing the loss and backpropagation are happening on the GPU. The decision about how to update the weights is basically your CPU doing something and then telling the GPU to update all the weights, and then you come back and do it again. Because those 2 pieces are the slowest part, those are obviously beneficial to be running on the GPU. So notes about batches and epochs. Traditionally, when you are training a neural network, what you will do is process a batch of training examples in parallel. You will compute their loss of all of the batch at once, and you will backpropagate them all at the same time. And then at the end of the batch, do a weight update, and then go to the next batch. So if your training set is 30,000 examples, you might do them in batches of 32 or batches of 64. And those batches are done one at a time. The batch has to fit in GPU memory. You can't subdivide the batch, because streaming in the data is basically not going to let the GPU stay busy the whole time. The whole training set doesn't necessarily have to fit on the GPU, although you will be paying a price for every batch you have to load on, because the connection between the GPU and the CPU is not as fast as the GPU memory is. It's different by like an order of magnitude. So the more of your data you can fit on the GPU, the better, but if you can't fit all of it, it's not a disaster. But when you are setting the batch size, you will get an error that TensorFlow ran out of memory if the batch is bigger than your GPU is. So on the other hand, if your batch size is too small, oftentimes the GPU will be underutilized. You need enough parallelism to keep that whole GPU busy. So oftentimes what I will do is basically crank up the batch size until I get the memory error and then back off one step, and that's where I run at. Training runs are basically in Keras, look sort of like what you might imagine. You can see it as it runs, through each round of the training data and each batch. At the end, it evaluates the validation data set that you gave it, just to give you sort of an independent estimate of where you're at. So one thing people often ask is, one GPU is great, more GPUs, are they better? And the answer is maybe, like all things really. And so what I mean by that is that how do you achieve the parallelism on the GPU? As what I would say is a data scientist who's not going super deep on the GPU hardware. So if you are working on Nvidia's self-driving car team, you can do a lot of crazy things. You can actually make your model split up to run different pieces of the network on different cards in parallel, but that is very sort of bespoke programming that you need to kind of dig deep in. As a sort of more new person, what is the easiest way to get parallelism? It's to cut your batch in half. So instead of doing 32, you do 64, you send 32 to one GPU and 32 to the other. This is a standard technique for using multiple GPUs. It doesn't always give you good utilization, in particular because once you run all the data through all the GPUs, you're like, great, I still have to make the decision about the weights. I have to bring the data together from both GPUs in order to make the decision about how to update the weights, and then propagate that back out to both GPUs and then go again. And so this last step sometimes can mean that when you're running this, your scaling is not linear. So I was doing some experiments with MXNet and Keras the other day, where I was getting pretty poor sort of sublinear scaling, where one GPU, was fine. 2 GPUs is maybe 30% faster. It wasn't 2x faster. Once I got up to 4 GPUs, I was finally 2x faster, but that's wasting 4 GPUs to get 2x the performance might not be cost effective. Of course, if you have them, use them, but you probably don't have them. So it's worth trying out, but don't assume that you're automatically going to get a speed up. And I put the function up there. Keras now, in more recent versions, has a nice built-in thing to take your model and split it in such a way that you get the 2 batches going through in parallel. This is just sort of a generic note about the notebook. The other thing you probably want to do in your notebook once you're done is make some plots exploring your results. Confusion matrices, loss curves, all kinds of things are useful for characterizing what how your model is doing, whether you need more data, maybe whether the network just isn't working. This is, again, not GPU specific, but it's a really important thing. The worst times I've ever had doing this were because I didn't look at my failure cases and I didn't look at the results of my data closely enough to understand what was going on. So again, you get through all that, rinse, repeat. You will never train a model just once. You may have heard people talk about hyperparameter scans. It's really a fancy name for doing lots of experiments with different knobs tweaked that aren't necessarily your training data itself. Things like batch size, learning rate options on the optimizer, size of the network, weighting of training examples. You can actually tell the training algorithm to pay more attention to certain examples over others, which might be useful if you have training data that isn't uniformly sampled across all the categories. You may have not enough samples of one category. You may want it to pay more attention to those samples. This is another reason you might want multiple GPUs, is because while the other case I was talking about of trying to use one training session on 2 GPUs that may not scale linearly, this will. It just means you have to set up the infrastructure to run stuff on 2 different GPUs. Okay, so that's about how you get started as an individual. Oftentimes I'm then talking to organizations who are like, okay, that's great. I tried this out on my laptop at home, but I'm a bank. I want to get going with this as a team. What do I have to think about? So the thing to think about if you have a team that's trying to do GPU stuff is that there's a couple of patterns that come up pretty quickly. One is centralized access to the GPU. These cards are not cheap. It's not usually cost effective unless your team is very small to put one in every data scientist machine. Often you will want to put them in some central location that you can timeshare between data scientists. And part of that is because not every data science problem needs a GPU. So if you put a GPU in every data scientist's computer, they might only need to use it 20% of the time, and the rest of the time it's just sitting there. So you can often get a lot better utilization if you put them in a central resource that you can sort of give access to your data scientists. Another thing to keep in mind, I get this question a lot, the best practice is to not let people share a GPU. You might buy this GPU that's got 16 gigabytes of RAM, and you're thinking, well, I only need 4. Could I share it with the guy sitting next to me? You're going to have a bad time. Don't do that. You generally, because of the way that time slicing works on the GPU, you usually want to have exclusive use for the GPU while you are training. And so this first problem, you're like, well, I put all the GPUs in one place. How do I do the resource management so that when I am using the GPU, no one else is? And that can be, honestly, as easy if you're a small team, you can just lean over and yell at your neighbor. But sometimes you want more automation to help you control that if you have like a whole sort of user facility. And then another thing, as I mentioned, is that you really need to think about your data science cluster having support for varying compute needs. Don't go all in on GPUs because you won't need them for everything. But you want some, and so you may want a heterogeneous cluster that has a mixture of GPU nodes and not GPU nodes. I'll come to then you have the problem of how to orchestrate that, but there are solutions there. However, if you might also want to just partition your resources and say, if you have a team that has extreme GPU needs, this is the GPU cluster and this is the not GPU cluster, and projects either go on one or the other. That's another way to solve the problem. So my employer, one obligatory note is that we try to solve the problems I've described here for companies using Anaconda Enterprise, which is basically a platform allowing teams to do data science in ways that allow them to share work with each other, resource acquisition, governance, IT people know what's going on. If you're air-gapped and need to get access to all these packages but don't want your people to get to the internet, our goal is to create a platform here that makes all those things possible. It's based on Kubernetes, so a lot of what I'm talking about is basically some Kubernetes functionality, but we've built a lot on top of it around packaging and other monitoring and all this stuff. So here's a screenshot of Anaconda Enterprise that's web-based, so your data scientist just needs a browser, and you've put all your GPUs in some cluster somewhere in a data center probably, and they can log in and they could create a new project. Each one of these tiles represents a project. The important thing, though, is that you can create a heterogeneous cluster to run those projects. And so in Kubernetes land, you basically have a couple of master nodes, and you have some worker nodes. And some of those worker nodes might have CPUs only. Some of those might have GPUs. And you basically, project by project, can decide this is a GPU project, this is not a GPU project. And then Kubernetes can schedule those things to run in the correct place, and also exclusively reserve the GPU for you for the duration of your project running, which is important. In this case, in our interface, it shows up as if you're starting the project and you pick a resource profile, your administrator could decide both how many CPU memory and how many GPUs is a profile. So we often have people describe them as t-shirt sizes. You would have small, medium, large, and then like large GPU or something. This is mapping directly down into Kubernetes resource limits. And so that's how, if you had your own Kubernetes system, you could do this sort of thing. However you solve this, there are many higher and lower tech ways to do this. You really just need to think about how to reserve and allocate resources for people for when they're using the GPU and when they're not. So the last piece I want to talk about is deployment. So the goal of all of this work was to get a model that worked, that met your criteria, that provided you some value, whether it's time, money, whatever, and then to get it into deployment, which means that it is running in some kind of environment that doesn't require the data scientist to manually hit enter over and over again. This is actually, maybe it's a REST API, maybe it's hooked into some other system. At some level, deployment depends on your organization, but that is an end goal for a production system. And the thing to keep in mind here is that best practices are evolving rapidly, unfortunately. There's still a lot of learning to be done here, but I could give you some of the questions that you should think about. One, and as I mentioned, this was in the beginning, what hardware is available in production? A lot of customers we've worked with have the GPUs for training in front of their data scientists. Their production servers are all just pure CPU based. That's fine, actually, and I'll talk a little bit about that. But you need to know that before you get started to decide whether or not you've hit your performance goal. Are you doing bulk processing or real time? So if you are, say, running a nightly job that's taking maybe thousands of loan applications and running them through some kind of scoring system, you can process those in bulk, which means that you might benefit from a GPU, because when you are doing the inference phase, so you did the training, when you get to the inference phase, the GPU will hit peak performance when you are classifying many things at the same time, but won't if you're only classifying one instance, one piece of data at a time. So if you're doing real-time processing, you might actually not even benefit from a GPU in deployment. As I mentioned, what is the performance requirement? How long are you willing to wait? Do you need the result to come back in milliseconds, or could you bulk process a bunch of stuff, and as long as the whole batch gets done by, in 5 minutes, that's fine. If after evaluating some of these previous things, do I need to optimize my model? Either for memory size or speed. If I'm going into a cell phone, I might care about memory size more. If I'm going into a non-GPU cluster, I might care about speed more. And then how should I package it along with dependencies? I don't have time to talk about that, but Conda can help you here. So this is a plot of a model I did real quick to show sort of what the scaling looks like as you increase the number of things. This is the inference direction. This is not training, this is inference. But as you increase the batch of things you'd run the inference on, initially the GPU is maybe only 30% faster than the CPU, and this is not a great CPU, with a batch size of 1. This is log 2, so that's a size of 1. But as you move up in doubling the size of that batch, very quickly the GPU becomes 10x faster. So you have to decide where are you on this curve. If you're back here, you probably don't get any benefit from the GPU. If you're up here, you might get a lot of benefit if you can batch stuff. I mentioned real quick, optimizing a model for size or speed is an active area of research. Once you've trained this whole thing, you might want to evaluate ways to make it smaller. Reducing the size of the input through downsampling or dimensional reduction might be important to shrink your network down. Reducing the size or number of layers using lower precision arithmetic. There are tools like Toco, which is for TensorFlow Lite, or TensorRT, which is specifically for Nvidia. So if you're going into like a mobile GPU or that sort of thing. So what's next? I would say the first generation of accelerated deep learning basically took advantage of capabilities the GPU already had. It was great at parallel linear algebra kind of tasks. The next generation, which is already in progress, this started with Pascal, is adding functionality aimed more for deep learning use cases. They saw the great benefits, and so they're putting more stuff directly in the GPUs, not really for graphics, although now they're using deep learning to accelerate graphics, so the circle has ate its tail. But things like tensor cores, increasing GPU RAM size, bandwidth improvements are all making it. These were added for a number of reasons. Tensor cores were added just for deep learning, basically, but these other ones have other uses, but they're all helping to address deep learning use cases of fitting more training data in memory, using lower precision arithmetic to go faster because deep learning doesn't need high precision, letting you scale out. So for example, better bandwidth between GPUs might improve that multi-GPU scenario by allowing them to exchange weights faster. And the other thing to keep in mind is right now NVIDIA is the leader, but AMD and Intel are eager to compete. They are working very hard, and so the state of things may change in a few years. There's also a new wave of deep learning specific chips. A lot of what I've said here will apply to those too, in the sense that they are an accelerator that you can put in your computer like a GPU to accelerate this use case. Although in the case of the Google TPU, you'll probably never be able to buy that. You'll always have to use that on Google Cloud. But Intel's got their own chip. Nvidia has actually open sourced the Verilog hardware spec for their own accelerator. Another thing that was mentioned in a previous talk actually is it's really great at the end of training to export a purely data description of your model. And PMML, for various reasons, has not been super great for deep learning, but everyone except TensorFlow basically has gotten on board with Onyx as an interchange format to let you export your model in a pure data way that can go on different accelerators. I don't know if Google will ever get on board with that. Regardless of all the stuff that's changing, it's mostly going to be transparent to you. The people who write TensorFlow and PyTorch and all of that are going to have to absorb all this technology and make it available to you. So you will basically, your net was that you'll see the cost of training and deployment go down. You'll either be able to go faster or to go the same speed for less money, which is great. So to conclude, deep learning is a powerful form of machine learning, but data science best practices still apply. Don't turn off your brain just because it said deep learning. You still have to do all the same thinking you did with all the old ways. GPUs dramatically speed up training and execution, and there are great software tools in Python. And there are many examples out there to inspire you. Seriously, Keras plus whatever is like the best Google search I've ever done. And Anaconda Enterprise can help you get started. There's our homepage. I'm happy to chat afterwards if you have specific questions about things. So thanks.